So we are ready. This one through. Okay, so this is going to be 7.7.1, and we would like to estimate. Okay, would like to estimate the probability of success P in the case of the binomial distribution. So that's the idea. Okay, so it's a 7.1. It's going to be called confidence interval for the proportion. So that's a confidence interval for a population proportion. Population proportion, which is going to be that P that we use in probability of success in the case of the binomials. But if you want to get a hint, this is the same as we would like to estimate. Okay, so we're going to estimating P, just refer to it, give it a hint in the binomial distribution. Binomial distribution. So that's the idea that we're going to get it. Now you see, I can give you the formula right away, but I would like you to justify the formula for you to give you a better understanding. That we did something with the mean. Remember, I just give you. We just try to use common sense to find it. So if you want to use the same idea, this is how we're going to do it. And at the end, we get the formula that give you, because there are a number of the new notation that I want you to be surprised. So let's see how we're going to do it. Remember, in case of the mean, we just find the sample mean, X bar, and then we extend it to mu, population, okay, population mean. In case of the proportion, it's the same thing. So your difficulty is going to be, in the case of the mean, it was mu and the X bar. In this case, this is P, the population proportion. So you have to create something. You have to create something similar for the sample, because you pick a sample and you find the P, probability of success. So you have to create something similar to the P for the sample, then you'll be able to get your estimation, okay? So I'm going to give you an idea how we're going to pick that one, okay? So let's just for a couple of minutes try to get the concept, and at the end we get a nice formula and then we're done. So let's see what we want to do. So there you are. We want, as usual, to estimate. We want to estimate the, okay, instead of that population probability of success, we refer to it as a proportion, because it's the same thing when you say 25%, 20, okay, 50%, it's a 50% of the full population. So what we want to do, we want to estimate the proportion, a fraction of the population, the proportion of the population, Okay, so the proportion of the population, of course, we can do it only by a sample, by a sample proportion. Sample proportion. So you need to have a sample proportion, and based on that one, you make a prediction for the result. So this is going to be sample proportion that is going to be defined. That is defined eventually. This is how we're going to define it. Defined by, you see that sample proportion we denoted by P hat. Okay, it was mu and the X bar, and this is going to be P and the P hat. Is defined by P hat. P hat is going to be equal to, P hat is equal to, it's going to be okay, it's going to be X or R. I go with the R, but I think if you want to use calculator, this is X. I'm going to explain it. P hat is going to be R over N. R over N. What is R? R, remember, in the binomial distribution is a number of successes. So this is going to be the P hat, okay, where we explain that N is the sample size. Okay, N is the sample size. It's going to be the sample size that you pick. Okay, a sample size, and R is going to be number of successes. Is the number of, as we did it before, number of successes in the binomial distribution, number of successes. Okay, and of course, when we have the P, the corresponding number was Q. Q was 1 minus P. Now that you have the P hat, it's going to be like for the sample, so we are going to have something like Q hat. So the Q hat is going to be 1 minus P hat. Okay, so these are the notation that we use for the sample. Because you have a sample and the proportion, a sample and the population. So you should, you should have two different notation. Now let's say we're going to be arrive at that confidence interval. We are looking for that percentage of error. Let's recall you are, of course, in the case of the binomial distribution. So recall that in the binomial distribution, mu is equal to the n times p. Okay, and you know that the sigma is equal to the what? The square root of npq. So if you want to copy the z formula for this case, you see that z was what? Z was x minus mu. That was the origin of the formula, confidence interval for the mean, divided by sigma. Now in this case, if you substitute, so that's going to be your x. Okay, that's going to be your x. The mu is np, so it's going to be minus np. And the sigma is the square root of npq. Okay, that's going to be the one. So what I'd like to do, I'd like to, if you compare it with I would like to make this one like the one that you did before. You have x bar minus mu over sigma over radical n. So what I'm going to do, I'm going to factor out the n here, or divide the top and the bottom by n. Both of them is going to be the same thing. So if you divide by n, you see what would happen. This is going to be x divided by n, and this is going to be np divided by n, and this is going to be the square root of npq divided by n, a little bit of algebra. So in this case, this n and n would cancel out. You see this n and n cancel out. So what you're going to end up is going to be equal to, this is going to be x over n, okay, minus p. You see this n is outside of the radical. If you want to simplify it by the n inside, you have to take this one inside the radical too. So it's going to be the square root. The top would be npq, and the bottom one, you take this n inside, so that gives you n squared. Like when you pull it out, you see, you take the square root of n squared would be n. That gives you the chance to simplify this too. You see, simplify it. So eventually you arrive, your formula would be like this. You see, your formula would be x over n minus p, and the denominator would be a square root of p q n. You see? Okay, now compare it with the formula that you did have for the mean. You see, compare this one with, compare. Okay, compare it with this formula. Remember the formula for the z? It was z equal to the x bar minus mu divided by what? Divided by sigma over radical n. We did this one for the mean. When it was for the mean, remember the part, the, the marginal error, we defined the marginal error was E equal to, remember, it was equal to the ZC, and this quantity here times it by sigma over radical n. That's exactly what we did, and we find out that estimation for the mean. So the formula about x bar minus mu, remember we just justify it, and you get this one. So if you compare it, you can create something for your proportion. If you compare them together, you see in this case what are going to have. So you can create the E again. So your E would be, because you're just using the Z, so this would be ZC again, times it by what? Times it with whatever you get on the denominator. The denominator gets sigma over radical n. In this denominator, we get this square root of, so it's going to be times it by the square root of, okay? So it's going to be a square root of, okay, PQ, okay? So, so on the top, you see P and the Q, you don't have the P because you are estimating the P. So what we're going to do, instead of the P, we go to the sample. So this is going to be P hat, Q hat, divided by N. You see? So if you compare them together exactly to whatever we did for the mean, you will arrive at the formula. The formula for the marginal error. So this is going to be marginal error of your estimation. If you say, look at this one, this quantity over here, x over n, is the one that we call it p hat. Okay, that's the p hat. So this means you can estimate the p. You can estimate the p by p hat, which is x over n or r over n, doesn't matter. So you can estimate the p by p hat with this marginal error. Okay, with the marginal error. So this is going to be what you are going to have. So if you want to find an interval for the population proportion, this interval is going to be less than p hat plus e, okay, and greater than p hat, okay, p hat minus e. So if you copy the structure that we did before, I'm going to write down officially for you. I just want to justify it so that you can, what is the origin of the formula that you are going to know to get over here. So we just copy the procedure for the mean, and we arrive at this one. This is going to be the confidence interval, for the, okay, for the population proportion with this marginal error of the E. You need only the ZC. The ZC, you can find it from the table. P hat is going to be X over N or R over N, and the Q hat, everything would be nicely done. Okay, so I'm going to make it official, write it down. Any question? It's just for you to understand it. In your book, they give you the formula right away. But if you compare them together, that's the same method that we did before, but with this version, okay? So make it official. That was all justification of the formula that I'm going to write it down for you now. But that should give you a better understanding of the concept. So that is going to be our conclusion. Confidence interval. Okay, that's going to be confidence interval for the population proportion, for the population, okay, population proportion P. Okay, for the population proportion P, and this is going to be the way we are going to write it down. That interval is going to be, okay, so P is going to be between P hat plus E, okay, P hat plus V, and greater than P hat minus E. Okay, P hat minus E, where what is your marginal error? Marginal error E is equal to the ZC times a square root of inside the radical P hat Q hat over N. You should write it down correctly. Everything is inside the radical when you want to calculate it. So that gives you the marginal error. Okay, in this formula, your P hat is equal to it's R over N, or if you want to use your calculator, the calculator goes with the X over N. Okay, R is the number of successes or the X, it doesn't matter, and it's a sample size. And the Q hat, you have to find it, it's going to be 1 minus P hat. Okay, that's going to be the case. N is sample size. N is going to be sample size. Okay, R or X, R or X, whatever you use, is going to be number of successes. Okay, this is going to be number of successes. And you know the rest. ZC is just a critical value. C is a critical level, and the ZC is critical number. It's the same thing that we did for the mean. Okay, and the E, of course, is marginal error. E is marginal error. That's it. It's a very easy situation, and the problem would be given. They give you only 3 numbers. The numbers are going to be the one for the X and the N and the C, confidence level, nothing else. And you find it quickly. It's a very easy case, and it's always the Z case, because you know that the binomial distribution can be approximated by a normal distribution. You know that if the sample size is going to be large enough, so we don't need a T distribution. Only it's going to be the case for the Z. Okay, any question? So read the problem carefully for your next quiz on the final, because the expression are almost the same as the mean. So read the problem to see which one is it. Is it ask you to do the population mean or population proportion? Don't miss it, otherwise it's a straightforward problem. Okay, any question? So let's do it. Give you one example, and then I'll show you if you want to use calculator. I'll show you how to do it. So this is going to be the example. Is the situation that we have over here is suppose we pick a group of students and we check their flu shots. So suppose 800 students. Okay, 800 students were selected. A student were selected at random. And they'd be given, okay, they'd be given shots to prevent shots to prevent a certain flu, a certain type of flu. Okay, so we have a group of 800 students and we give them the shots. So what's the question? The question is going to be, suppose out of this 800, 600 of them, suppose 600 of those students of them did not get the flu. Did not get the flu, yes. Did not get the flu. So this means the shot were effective. So 600 out of 800. So the question is, we'd like to find the confidence interval. So find the 99%. Okay, find the 99%. 99% confidence interval. Confidence interval. Confidence interval for the population. For the population. For the population proportion. Population proportion. Okay, of the students. Population proportion of students who didn't get the flu. Students who didn't get or did not get the flu. That's it. So as I told you, you read the question carefully. You find out this is confidence interval for the proportion. If it's going to be for proportion, you're just looking for three numbers. You see two numbers given to you. It's 800 and the 600. So the 800, the bigger number is going to be n, the sample size. 600 is number of successes. You may call it X, you may call it R. Quickly enable you to find the p-hat, okay? And the only other number that you have is going to be the confidence level, nothing else. Okay, are you ready? Solution. So the question is regarding the proportion. So what is my sample information? Okay, sample data. I like you to write down this form. So the sample data would be sample size, the bigger number, 800. Probability, number of successes. I go with the R or X. R is 600, like in probability binomial distribution. Okay, so the confidence level of 99%. So I want to find the error. That's it. I got to find the E. Okay, so we know the formula. So we have to create, find the thing that we have. Okay, it's just to remind you that this is the formula that we're going to use. You have to find your error using this formula. E equal to ZC square root of inside P hat Q hat divided by N. Okay. So you have to go and back and bring the ZC. So C of 99%, 99%. You go to the table that we gave you before, okay, that bottom corner one, and you find your ZC. ZC for the 99% would be 2.58. This is going to be ZC. Then you have to find the P hat and the Q hat. Okay, I find it here so that you can see it. Then I go to the next page. So I have to find the P hat. P hat is going to be R or X over N. So in this case, the smaller numbers goes on the top, 600, and the larger numbers here. 600 over 800, that give you 6 over 8. You can simplify it, and that give you 0.75. So the P hat is going to be 0.75. So that's going to be a P hat, which is 0.75. Then you have to find the Q hat. Q hat is going to be 1 minus P hat, which is going to be 0.25. You have to find all these. So we have everything we need, the ZC, P hat, Q hat, and the N. So we're going to substitute here to get the E. Okay, any question? So I'm going to continue on the next page if you are done. So we have to drop these numbers all in to get the E, and then write the confidence interval. Okay, so this is going to be the result. If you substitute into the E formula, so E is equal to the ZC is 2.58, and the square root of, on the top, P hat, Q hat, so it's going to be 0.75. Okay, it's going to be 0.75 times 0.25. Okay, divided by N is 800. 800, and you put them together, so the result would be 0.0395. That's going to be your marginal error, usually rounded at the end. Okay, so that would be the marginal error. You can check it with your calculator. Now we are ready to give you the interval. The interval is P hat minus E less than P less than P hat plus E. So the P hat was 0.75. So it's 0.75 minus 0.0395 less than P less than P hat again, which is a 0.75. Okay, plus E, which is a 0.0395. And if you simplify it, so let's give it something like 0.71. And this is going to be 0.79. I just rounded a little bit. The proportion must be given in percent because this is probability. Okay, so this is going to be, the case is 71%, and this is going to be 79%. And of course, you have to make a comment. So the comment is going to be confidence level was 99%. So there is a 99% chance. 99% chance that the population proportion are going to be between 71% and 79%. So basically this means for those population who got the flu shots, there is between 71% up to the 79% chance that they are not going to get the flu. Okay, so just make a comment regarding to the level that we have. So for example, this is one of them. So we can say that there is, okay, there is a 99% chance, okay, chance that the population proportion, okay, population the population proportion, that's one, population proportion is going to be between, okay, so it's going to be between 71% and 79%. That is going to be the final answer. Very easy procedure for the population proportion because it's only one case, and if you put all these together, then you know that would be fine. Any question? It can be done by the calculator. Okay, I'll show you, but you have to explain it. Remember, you set up the problem and then the calculator. So are you done? So let's see if you want to do it by your calculator. This is the one. You have to go to the test to find it, like the one that did for the Z interval. Let's see if I remember when I got this one. So you go to the second and get the statistic. Okay, then I need the tests. So that is going to be the test that we used before. Remember, we used 7 and 8 for the, okay, remember this is the one that we used for the Z interval. That was for the Z interval. If we go down, that would give us the, okay, Z interval. That was a T interval that we use again. For the sample proportion, you get quite a number of them. This is for 2 samples. You must go for 1 sample. You see, if you go, that's a 2, 2, and this is the one. Okay, 1 proportion, because you can compare 2 samples together. That we are not going to do it. So you go with this one, 1 proportions, and if we click, so this is the information that they are going to ask you. In your calculator, they call it X instead of R. So you are going to submit it. In this case, X was 600 total portion of the students. Okay, N is the sample size, the bigger number. The bigger number was 800. So that's 800. Then the level was 99. So this is 99. And then we are going to calculate. That's it. 0.71, 0.710, this is the interval, starting from 0.710 up to the 0.789. You see, my answer is 79. I just run that. So the interval is going to be between 71% and the 79% based on this information. So it's very easy to use calculator, and we don't mind. You just set up the problem, show that, write your formula that show us that this is related to the proportion that you are going to find out, and then you can use your calculator and give us the answer, and we don't mind. Okay, any question? So this is it. Again, I tell you that you have to go to the, okay, you go to the test, and this is it, the statistic, then the test. The tests are the one that we did before. Okay, number 8 and the 9 is 7 is the Z interval that we did it before. T is the one that we use for the proportion, not this one. It's a 2 sample, we have only 1 sample. So that is the one. 1 sample proportion Z test. We are not going to have any T because we use the binomial approximation. Okay, so this is the one, you click. X is the same as the R, N is the sample size and the confidence level, and then you calculate, and this gives you the interval, and you're done. Okay, so it's very popular case, the proportion, when you do it in everyday life. The problems are mostly proportion. Okay, so this is going to be the case that we're going to have. I have another one, I can do that one too quickly. Just get the idea. There is a problem of a sample size for this one. It's very similar to the sample size for the proportion, for the mean. And we don't want to be confused. So we're just using, I'm not going to use that one. This is a new one. Okay, so let's have quickly give you another one. So let's check the calculator again, just make sure you have it. And we are done with this section. Okay, so let's have a quick one again. Example for the proportion. We give you one proportion on your next quiz and one on the final. Okay, so over the weekend I will try to post for the quiz 4, the practice quiz for number 4, and I guess idea. So I may also post the final review so that you know that which sections or which topics are going to be given. We give you that just a distribution to start with the normal distributions, nothing from the first part. Just, but we just get the box plot from the first part, nothing else. Okay, so let's give you another one quick. I want to check this one with calculator as well. A random sample. Okay, a random sample of 188 books. Okay, books purchased. Books purchased at a local bookstore. At a local bookstore. Okay, show that show that 66 of the books, okay, 66 of the books, 66 of the books were murder mystery. Okay, murder mysteries. Okay, so the portion is going to be 66 out of 188, two numbers, right? The bigger number is always the sample size, which is n, the smaller number is going to be r. So what's the question? The question is, would like you to find the 90% confidence interval for the proportion. Find a 90% or the 90% confidence. Okay, confidence interval for true proportion. True proportion or the population proportion is going to be the same thing. Okay, for the true proportion, true proportion of the number of the true proportion of the number of sold murder mystery book. Okay, murder mysteries books. Okay, so information quickly can be collected. Okay, are you ready? So that is it, is going to be the solution. So we are looking for the proportion. So I need information. What is sample information, sample data? So the sample data is start with the sample size. The bigger number, n is equal to the 188. Number of successes, R is going to be 66, the portion that you are aiming for. And the confidence level is 90%. So you are looking for the percentage of error, marginal error. Okay, for the marginal error. And as usual, you have to find the EC. Okay, so your formula for the EC, remind yourself that your formula must be ZC square root of P hat Q hat over N. So we are going to find the ZC, okay, in the table. C of 90%, give you the ZC is 1.645 for the 90% in the table that we have, So that would be the ZC. We have to find the P hat. So the P hat is the proportion R over N. R is 66 and N is 188. Okay, if you divide, that should give you 0.35. So that give you P hat. And you find the Q hat, which is a complement, 1 minus P hat. And that give you 1 minus 0.35, which is 0.65. Okay, 0.65. I'll go back, substitute to get the E. That's the E, not EC. Okay, I want to go to the next page. So I'm going to substitute here. E is equal to the ZC square root of P hat Q hat over n to get the marginal error. Done, ready. So getting the E. So the E substitute, your ZC is 1.645, 1.645. And then we get the square root. And on the top, we get a 0.35. Okay, 0.35 times 0.65. Okay, and divided by 188. And calculator to get this one is going to be 0.0572. Okay, so that gives you your marginal error. So the marginal error is going to be almost 5% or 6%. So that's going to be the E. Okay, you go for the interval, it's a proportion. So P less than P hat plus E and greater than P hat minus E. We substitute, it's going to be 0.35. Okay, 0.35 minus E, which is 0.0572 is the less than P, and the less than 0.35 plus 0.0572. And we simplify it so that we have 0.29 less than P and less than 0.41. In percent, 29%. Less than P, less than 41%. That's it. So there is between 29% and 41% chance. Okay, that you can say that this is the actual one is there is 90% chance, 90% chance that between 29% and 41% of those books that were sold at the bookstore are going to be are going to be murder mysteries. That's that's one interpretation. Or you make a you make a comment, different formats. You can say that one can be sure, or one can one can be 90%, or there is a chance. One can be 99% sure that the population proportion, population proportion is going to be between, it's going to be between 29% and 41%. It's that easy case, the proportion. Any question? So let's check it with the calculator to make sure we did it right. So this is it. You go the second statistic and you need the test. That is going to be the test. The test is going to be 1 for the proportions. That's 8. Then not this one, 2 proportion. We need only 1 proportion. That's it. Okay, it's kind of number 11. So I need the X and the R are going to be the same thing. In this case, R is 66. The total population is 188. So that's going to be 188. The level is 90. The level of 90. And then we are going to calculate. That's it. Between, that's it. Between 29.2938 and 40.8 is the one that I rounded into the, between 29 and 41. And that's 29% and 41%, the correct answer. Okay, so that's a proportion. Any question? So we are done with the confidence interval for the proportion, and we already talked about confidence interval for the mean, and we have one more to go, and that would be a standard deviations. Okay, so in the case of the standard deviation, we need a new table. Okay, I posted this one for you. So I'm going to describe it, then I give you a break if you want to, have a look at it or make sure it's ready, because we need that one to be able to explain it to you. Okay, so let me show you what I posted. This is the one that we need. It's going to be called chi-square. It's chi-square table. Okay, chi-square distribution. That is going to be the chi-square. So remember, in the case of the z, we use the z-score. In the case of the t, we use the t-curve. In the case of the standard deviation, we have to use the so-called chi-square distribution. This distribution depends on the standard deviations and the sample size, and there are going to be some differences between this one and the other two that we did. The notable one is that this is not going to be symmetric. The one that did before was symmetric, okay, about the mean. This curve is skewed. It's skewed to the right. As you can see over here, is skewed to the right. And this is one. The other one is, but the area under the curve is going to be still 100%. Since the area is 100%, so we can use it for the probability. And the other difference is going to be that when you read the z or the t distribution, the number on the table, they refer to the area to the left of the z number or the t number. But in the case of this distribution, the number will refer to the area to the right, not the left. So this is two different, okay, differences between these two together. So I'm going to describe it, then I give you a break so you can have a look at this table. It's posted, I think on the front page you will see the chi-square distribution, and then we come back and we do it. So let's give you a description of this one first. Okay, any question? So we are done with the 7.1 and the 7.2. And this must be, I think, 7.3 in your book. Okay, so you can check it again. It should get there. It's all right. Yes, that is estimate of population standard deviation 7.3. That is correct. Okay. So let's describe this new distribution. So get the idea of this one first. But the actual result is very easy, and it's much easier to use. Do it directly rather than calculator. Okay. But you can check that one also later. So what is this? This is it, confidence interval. You get 2 questions from this one on your next quiz and the final. So what is going to be confidence interval? Confidence intervals. Okay, we can do the standard deviation, the variance at the same time. That's why we call it confidence intervals. For variance, population variance, and variance and standard deviation of a population. Standard, okay, standard deviation of a population, Okay, so that's going to be the idea. Now we need to introduce that a new, okay, new distribution. This new distribution is called chi. This is how we're going to pronounce it, chi-squared. Okay, it's going to be chi-squared distribution. Okay, chi-square, I should use another color. Okay, so it's going to be chi-square distribution. Now, how are we going to define it? If here the variable, as usual, is x, if the variable, let's be variable, the variable x is normal, is normally distributed, with the population standard deviation, with the population standard deviation, as usual, mu sigma. Then for a given sample, for each sample, this curve would be changed. It's like a t distribution. Okay, so for a given sample size n, okay, and the sample standard deviation, and the sample, okay, and the sample standard deviation. You know that sample standard deviation is going to be lowercase s. Now the chi-squared. The chi, that's chi square distribution. Chi-square distribution is defined by, that's it, the notation, you see chi square. So this is how we write chi. Okay, chi squared is equal to the n-1 times s squared divided by sigma squared. S is the sample standard deviation, sigma is the population standard deviation, or s squared is the variance, sigma s squared is going to be sample variance, and the sigma squared is going to be population variance, okay, whichever you like to call it. Okay, so this is it. So, previously we have the z defined by, x bar minus mu, divided by sigma over radical n. We have the t, remember, x minus s over, or x bar minus, it was the t x bar minus mu over s over radical n. Now you have the chi squared, n-1 s squared over sigma squared. Now, as you put the numbers in, then there is going to be a curve, this curve, okay, the resulted curve, if you like, or resulted distribution. The resulted distribution. Okay, the resulted distribution is going to be called, okay, it's called the chi squared. The chi square distribution, or chi square curve distribution. Okay, so this is going to be the one, like, we have the normal distribution before. Now we are going to have a chi distribution to get these numbers done. Okay, so this is going to be the case. So, so the curve is going to be like this one. You see, this is going to be the curve that we have. Okay, So, it's going to be skewed to the right, skewed to the right. And if you change the sample size, okay, if you change the sample size, you're going to have different curves. So that's why, like the t-distribution, if you want to identify this one, we're going to be identified by degrees of freedom, and that we are going to have. Okay, so that's going to be, again, it's not going to be a unique one as we did with the, okay, normal distribution. Okay, I give you a break now, and then we come back and we get the property of this one. If you would like, we can look at that the table, the chart that I posted for you. Have a look at it. If you can make a copy, or just make sure that you have it, because I want to explain on it. So we can try it. Then we continue. I've already rearranged some of the assignments according to the new timetable that we have. I checked them again over the weekend, or if anything is need to be adjusted, I do it again. Okay. So let's have 10 minutes. We come back and we try to finish this one. We have to understand the curve, otherwise the final formula is very easy. There is no marginal error, and directly we can get the formula right away. Okay. So it's almost 11:20. Let's have about 10 minutes. We come back and we finish it. See you then. Okay, so let's continue with the description of the chi-square. Okay, so this is the variable, the resulted numbers, the collection of the data values that we have, create a curve for us. Okay, so we're going to describe this curve like the Z curve that we did before, or the T distribution. So some notes regarding the use of this curve. Okay, so we continue that note that generally I just list the one that is going to be useful for us. Okay, so the first one is the big difference is this is not symmetric. Okay, so the chi-square curve is is not symmetric. Is not sorry, is not going to be symmetric. Okay, it's skewed to the right. It is okay, it's going to be skewed to the right. So that's a big difference when you compare it with the others that we did have. And the second one is the shape of the curve would be changed if you use different sample. So you have to assign a number to the curve to call it, to find it. And that number, of course, is going to be degrees of freedom. Okay, so it's like the T distribution. You have the degree of freedom. So the shape, okay, the shape of the curve, depends. Okay, depend on the sample size or the degree of freedom. On the degrees, okay, degrees of freedom. Freedom df, where you know the formula is going to be the same as before. So the df is going to be equal to the n minus 1. So that would be the case. So if you want to use the table, you have to find the degree of freedom first. Okay, and the other things is number, you know, it's as usual, if n is going to be a large number, if n getting bigger and bigger, this distribution would be nearly symmetric. So that's a number 2. Number 3, the chi-square number is always positive. It's not because it's a square. This a square is just a name. Okay, it's not a power. This is not a power. It's just a name, chi-square. Okay, but the value cannot be negative. Okay, so the values of chi-squared, this distribution that have are going to be all non-negatives. It can be 0, but it cannot be negative. Okay, it's going to be non-negative. So your chi-square must be always a positive number. So if you get a negative number, probably you made a mistake. Okay, that's number 3. And number 4 is that we can use it for probability because the area under the curve is 100%, which is like 1. Okay, so the area under the curve, that curve, area under the curve is going to be 1 or just 100%, which is good. We can use it for the probability in future. Okay, that's it. 1, 2, 3, 4. Any question? Now the 5th one is the one that we are going to be interested in. The 5th one is how we're going to identify those. Remember, for the z-test and the z-test, we did have the critical value, which is the one that's going to be useful for us when you want to, okay, do our estimation. So we are going to find out what is going to be the, okay, so what is going to be the critical value for this case that we have, okay. Let's see if I can manage this one in this board. Oh, let's go back to the original. Okay, so for the number 5, this is the number. So there you are. We are going to use the notation. We want to create something like ZC. So we use the notation. Okay, we use the notation chi square alpha. This alpha is going to be a number. Okay, we use this one to denote. Use this one to denote the critical value, like the ZC that we did before. The critical, okay, the critical value. Okay, such that that's the difference, another difference between this one and the other one, such that the area, okay, such that the area and the chi square, and the chi square, and then the chi square curve, okay, to the right, of this number, this values chi square alpha is going to be equal to the alpha. Okay, it's like when you use the z number, you see when z was equal to 2, then when you want to find the probability, you just get the area to the left of the z equal to 2, the area to the left of the 2. In this case, you are going to pick the area to the right. This is the only curve that you go with the area to the right. For the t distribution is area to the left, and for this one also the same thing. Okay, so this is going to be the case. So that's going to be the case that this is going to be your chi-square table curve. Okay, if you pick a number here, which is going to be chi-square alpha, okay, then this number would represent this area, which is alpha. Alpha is going to be like a percent. Okay, if you know this is going to be the percentage because it's going to be probability, percentage probability. So in the case of the z, it was the area to the left. In the case of the chi, it's going to be area to the right. Now, since this graph is going to be skewed, then you are going to have two different value for each chi square that would be given to you. One of them is going to be called the right, the other one is going to be called the left. So there are two different, two different values of chi squared. Okay, we call it the right side, and the other one we call it and the left side, and they are going to be denoted by, we use these two notation to identify it. And for the right side, we use chi squared r stands for the right. Okay, so this is going to be the right, and we are going to use the chi squared l represent the left, so this is going to be left. Okay, so we have to get to know these expressions that we're going to have, chi squared to the right, chi squared to the left, and we are going to see it in a minute by using that table how we're going to get these numbers. Write it down, then I give you the example how we're going to do it. So what do you want to get these numbers? Okay. Somebody wants the other page. I'm going to show you in a minute. This is the end of the other page. Somebody wants to take a look at it. That's the one. So the property of the chi-squared is not symmetric. Okay. It's different from different numbers. So you have to use the sample degrees of freedom to identify the specific that you are going to be interested in. It's never negative. It's always positive. And the area under the curve is always 1 or 100%. Okay, 100%. And when you want to read to get the critical values, there are going to be two types. The critical values to the right and the critical values to the left, that I'm going to show you how you are going to find. Okay, so let's get one example to see, because this is the only thing that you're going to do for solving the confidence interval for the chi-squared. So let's find out how we can use the table to find these two chi-squares. Okay, so this is going to be an example. I'll go to the next page because I need more rooms. Talk about it. So let's see how we're going to do it. So this is the example. And we would like you to do the following for us. Okay, would like you to find, okay, find the values. Okay, find the values for a chi-squared to the right. Okay, and chi-squared to the left, L. Okay, for a 90%, for a 90% confidence level, okay, when the sample size is 16. Okay, we want to know how we're going to find these two numbers that we talk about, chi-squared to the right, chi-squared to the left. They are just critical values, like the ZC or the TC that we did before. Okay, this is how we're going to set up this one solution. You have to find those cut points, if you like, for these two numbers. So you're going to get the curve. You say get the curve, and just identify that 90%. Let's get a 90% of this curve. Suppose this is going to be 90% of the curve. Okay, so it's going to be 90%. Okay, it's going to be 90%. So the leftover, you see this is 90%. The leftover is going to be 10%. So the 10%, these two together must be a 10%. So if you divide it by 2, each portion is going to be 5%. So this portion over here is going to be 5%. Okay, and this portion over here is going to be 5%. Okay, so 5% to the right, to the left. Now for the chi-squared to the right, so you are going to consider this number, like the Z curve that we talk about it. You see this is going to be 5%. So you want to find the chi-squared that give you the area to the right to be 5%. So this is the one that we're going to be interested in. Okay, so this is Z if you like, but in this case it's chi-squared. So this number over here is going to be chi-squared. It's chi-squared of the 5%. Alpha is just 5%. So we write it as a chi-squared of the 0.05. Okay, so if you identify this number, so in this case, that number would represent the area to the right of the chi-squared, which is a 5%. Okay, this is going to be your chi-squared to the, okay, so this is the same as the chi-squared to the right. Any question? Now consider this cut back here. So this area is 90%, and this is 5%. So from here right to the end is going to be what? 90, and 95%. So this number over here is going to be the chi-squared, or the number that would represent this 95%. The 95% would be 0.95. It's a probability, okay, percentage or the probability. So this is the one that we refer to as the chi-square to the chi-square to the left. Okay, so the chi-square to the right is this one, this cut point over here, which would represent the area to the, okay, area to the right, in this case 5%. And the other area to the right is going to be 90% and 5%, 95%. So for the 95%, this portion is the one that we are going to be interested in. That is going to be chi-square of the 95. Okay, any question? Now get back to this table. Now we're going to read the table. You see, this is called chi-square table. So these numbers on the top here, you see, these are your alpha, that confidence level that we did have over here, okay? So you have, for example, you start from 99.5%, this is a 99%, 97, 95, you just keep going. You see that give it the 10%, the 5%, 2.5%, and 1%, etc. And this column is a degree of freedom. Okay, so this column is degree of freedom. And you know that you can make a note for yourself, again, that the degrees of freedom, df is equal to the n minus 1. So in order to get this chi-square to the right, to the left, you find the degree of freedom first. Okay, so in this case, you see n is equal to the 16. So n is equal to the 16. So the degree of freedom, d of f, is going to be n minus 1, which is equal to the 50. So what you're going to do, you go to that table that I talk about it. So this is the table and this is the degree of f. So we're going to pick what is the 15 is. This is the 15. Okay, we got the 15. Then we go to the right. You see, you go to the right and look at this top for the alpha. Okay, so look at this one that we have over here. So this is what we got here. You see, we identified the f of 15. So where is that? The f of 15. Okay, this is a degree of freedom for the 15. Okay, this is it. This is going to be the 15 that we have. Then you look at the top for the alpha. You see the top for the alpha. This is your alpha, and you read these numbers. The first number that you need is the chi-square to the 95%. So look at this one. So this is 99%, 97%, 95%. So this is 15. This is going to be 15. You see, this is the f of the 15 and the 95%. The number that you can see over here is this one. The number is what? The number is 7.261. This number is going to be what? This is going to be chi-squared to the left, or the chi-square up to 0.905. Okay, if you compare it with the one you have over here, you see that's 1. So this is your first number. Chi-square of the 0.95 would be equal to the 7.26. Then you continue to get to the other side, which is the 5%. So continue on that column again. You see that's you continue with the top, on the top, the alpha of 5%. This is alpha of 5%. So we get to the alpha of 5%, you read this number. So this number is going to be chi-square to the right. And the number is 24.996. Okay, so since it's skewed to the right, the number to the right is much higher than the number to the left to get it true. Okay, any question? So if you're going back to what we did here, so we start moving, we're moving the 15 and we compare it with the alpha on the top. So your alpha on the top here, alpha is equal to the 0.95, 95%, and you read this number. This number is 7.261. And then you continue. You continue to get to the next alpha. The next alpha is going to be 5%, which is going to be 0.05. So 0.05, you read this number. And the number, as you saw, it's going to be 24. Okay, 24.996. So this is the chi-square to the left, L, which is 7.261. And this is going to be the chi-square to the right, which is 24.996. And then you're done. Very easy procedure. See, it's easy. You don't need any calculator to be able, to find it. And you need this one to be able to take care of the theorem that we have. Okay. No, it's not 8.545 because it is 7261. You see, that's the one. df of 15. You see 95%. The other one that you talk about is 90%. Okay, for the 95%, okay, this is 95%. This is 95% and this is 90%. So the one we are interested in is 95%. So for the 95%, we get that 7.26261. Okay, any question? It's very easy procedure to find. We can find another one. Just make sure. This is the only thing we do. We give you the formula, then you substitute, then you're done. Okay.
So does that represent area?
Which one? No.
Does the chi-squared represent
no.
area?
This is like the critical value. You see, this number, the area.
It's like a z-score.
Yeah. You see, the area corresponds. The area corresponds to the 7.261. Chi-square of the 7.261 is 95%.
Okay, gotcha.
Okay, that's one. So let's get another one. Just make sure that we have no difficulty, and then we give it the actual formula, and then we're done with this one. Let's try another one with n equal to 20. I'm going to use both of them in examples I'm going to give you. N equal to 20, the confidence level of the 95%. Okay, 95%, and we want to find the chi-square to the right and the chi-square to the left for this one. Okay, so we have to divide to get those numbers. Solution. So this is going to be a curve. So I pick the 95% in the middle. So if this is going to be 95% of the curve, then I need to identify this bottom, this cut point here. And so this is 95%, you divide it. The leftover is going to be 5%. So divide 5% by 2, then you 2.5%. So this would be 2.5%, which is going to be 0.025. Okay, so here you want to find the chi-square of 0.025. And over here you have a 2.5% again. So we have a 95% and the 2.5, 97.5. So this would be the chi-square of the 0.975. Okay, be careful. There's one case that it's a 99%. That's a tricky one because this is going to be 99%. So the leftover is going to be 1%. So this is going to be 0.5% and the 0.5%. Make sure you get to know this one right. Okay. So we go to the table, n is equal to 20. We get the df of a 90. Okay, so the df is 20. Sorry, n of the 20. So the df would be 19. Okay, so you get the df of a 19, then you move on the top. You have to get to the first alpha, which is going to be 0.975, and then you continue to get the 0.025 to get these two numbers here. Okay, so this is the table and the df of 20. Okay, this is df of the 19. Okay, this is going to be df of the 19. df of the 19, and the first number was 97.5%. This is the 97.5. This number is 8.907. Then you go to get to the 2.5%. You see that is going to be 2.5%. The number, the right one must be much bigger than the other one. So that should give you 32.852. So the chi-square to the left would be 8.907, and the chi-square to the right would be 32.852. So I bring it up here. So this is what I got. I got the 8. Okay, that's it. This is 8.907. And this is the 32.852. So this would be the chi-square to the left, chi-square L to the left, which is 8.907. And the chi-square to the right is going to be 32.852. That give you the numbers. Okay, the chi-square to the right is much bigger because it's skewed to the right. Okay, if you have something doing those disciplines or majors related to the health, okay, medical school, etc., nursing, they are interested in this one. Mostly they work with the confidence interval for the standard deviation. They compare different substances together. So it's used quite a lot, and there are a couple of more tests related to the standard deviation, but they don't need the mean or the proportion. So just pay attention to this if you are going to do something like that. Okay, so now we are ready to give you that confidence interval. Okay, so we get to know it, and this is going to be the actual confidence interval formula. It's a straightforward formula, and it's quite different from the other that we did, and you can't miss it because it's just one case. Okay, so there you are. This is the formula. What is confidence? Okay, what's going to be confidence interval? Confidence interval. We go with the variance first, sigma square. It's easier, then we take the square root. So the confidence interval for the population variance, of course, sigma squared. Okay, and this is the formula. It's going to be sigma squared is less than. Is less than, the top is just like the chi-square variable, n minus 1 times it by s squared divided by the chi-squared. But you are on the right, but you have to use the chi-square of the left, L. Okay, on the other side, the top is the same. It's n minus 1, okay, n minus 1 s squared. Then this is going to be chi-square again, but you are on the left, but use the right. And it's clear because you see the chi-square to the right is a larger number. So when you have a larger number here, because the top are the same, then this fraction would be, the result would be less than the other one. If you miss it, it's not going to be your interval. If you switch the numbers, this number must be less than. If you use the chi-square to the left here, the number is going to be bigger. So just think about it. It's the left, you use the chi-square to the right. And this is right, you use chi-square to the left, okay? So this is confidence interval for the population variance. You take the square root, that gives standard deviation. So we usually write this one first. So confidence, okay, confidence interval for population standard deviation, which is sigma. Okay, we just take the square root of the top that you have. Okay, it's going to be the square root of n minus 1 s squared, and this is chi squared to the right, which is going to be less than sigma, and this is going to be less than n minus 1 s squared, and divided by the chi squared to the left. Remember, these squares are name. Okay, this is just a name. The value is the one that you're going to get from the table. But when we get the s, you have to square it. Okay, just make sure you know. But the other one is just a name of the chi square when we say. You see, it's easy formula, but the main part is to find these two. To find the chi square to the right, to the left. You can get it from the table right away. And just put these numbers away. Okay, and you have a number of the assignment in your book that they ask you to just find those two numbers, the chi square to the right and to the left. So you must know how we're going to do it from that table. We prefer the table because we want to make sure you understand understand the topics. So you have to bring the table to your next quiz and the final. Okay, there you are. Example. The examples, you can't miss it. They give only 3 numbers. You see the sample size, sample standard deviation, and the confidence level. That's it. Nothing else. You don't need anything else. So as soon as you be given those, you are going to go to the table and find the chi square to the right, to the left. You bring it here, and then you're done. Okay, so there you are. This is an example. There are going to be 2 types of examples, like the t distribution. There is one that they may give you the actual numbers. Then you have to find the standard deviation yourself. Okay, so let's check this one. We are going to look at the sample of the disposable camera batteries for this problem. So what's the question? The question is find the 90%, find the 90% confidence. Okay, confidence interval for the variance. Okay, for the variance and standard deviation. And standard deviation. Standard deviation for the lifetime. The lifetime of disposable camera batteries. Disposable camera camera batteries. Camera batteries, if we have the information regarding a sample, if a sample of 16 disposable 16 disposable camera batteries as a standard deviation, a standard deviation of 2.1 month. Okay, we pick a sample of 16 disposable batteries, and we find out their standard deviation is 2.1 months. So based on this information, we want to make a a prediction for all the disposable batteries, camera batteries, to see what's going to be the lifetimes, average time. Okay, so you read the problem carefully. Is it related to the standard deviation or the variance? So you have to set up your information. So the sigma is missing. So I need the sample information. So it's going to be sample data. So the sample data, I start with the sample size. We have the sample of 16. Okay, and that's it. So I need the sample here, the standard deviation that would give you in sequence 16 and the 2.1. So S is 2.1. And you want to do it by the confidence level of the 90%. That's it. As I told you, this is the only information that you be given. So we have to go and find the chi-square to the right, to the left, because we know the formula. Okay, so we have to find the chi-squared to the right and the chi-squared to the left. It's the one that we did. Just quickly remind you, but I write the numbers. Okay, so it's the same thing, 16, the previous example that I did. So you have to go and find it. I just remind you, you have to find this. So that would be the 90% that we talk about it. And that is our 5%. And the 5%. So over here, we are interested in the chi-square of 0.05. And over here, chi-square of the 0.95. Okay, and we did find this number, so I just repeat it again. So the number was chi-square to the left was 7.21, and over here the chi-square to the right was 24.996. So we have to find these two for each problem that we have. Now we get the formula. That's it. This is the formula. And you substitute because you have all the information that you need. Okay, we go for the variance first. So the variance formula n-1 s squared divided by the chi-squared. You see you are on the left, but this is chi-squared to the right, which is going to be less than sigma squared. It's going to be less than, the top is going to be the same, n-1 s squared. And this is going to be the chi-squared, but the chi-squared to the left. You substitute n is 16, so it's going to be 16 minus 1. S is 2.1 squared divided by chi-squared to the right, that larger number, which is 24.996. Okay, this is the one, so it's going to be less than sigma squared. The same thing on the top again. 16 minus 1 times 2.1 all squared, but the chi-squared to the left, the smaller number, 7.221. And we just use calculator to get these numbers. So I have 2.65, which is less than sigma squared, and that's a 9.11. So this is the confidence interval for the variance. Take the square root. Okay, we take the square root. It's a 2.65 sigma, and that gives you a square root of 9.11. Again, use your calculator. So I have 1.63 less than sigma, and this is going to be less than 3.02. So that gives you the confidence interval for the standard deviation. You have to make a comment. We usually make a comment at the end. Remember, confidence levels was 90%. So we are 90% sure that the population standard deviation of all the, disposable batteries of the cameras are going to be between 1.63 up to the 302 months. Okay, so we have to make a comment. Make sure you do it. So there is a kind of 90% chance, 90% chance that the standard deviation, okay, standard deviation of the population, of course, population is there. Population standard deviation, population standard deviation is going to be between these two numbers, okay, 1.63 and 3.02 months. Okay, that's a month. Okay, so the basic, to prepare it, it takes times, but at the end, it's very, very nice case that we're going to have. And that's the case one for the problems. The case two, as I told you, is that they may give you all the information. You see, they give you data set like the t distribution. Then you are going to have extra job. The extra job is you have to find the standard deviation, sample the standard deviation yourself. You find the S, you know that you can use your calculator or just the PDF formula that we did. Okay, I'll talk about that one for you next time. So we are not going to cover anything else. We did, the confidence interval that we need. So we did the mean, two cases, the proportion, and the standard deviation. For the rest of the course, there is another concept that, you see, we did this. You see, we got this interval. So we predict from the sample what is going to be there. Okay, the same characteristics for the population. The next step is somebody may challenge you. You see, when you say that the population standard deviation is going to be something like less than 3.02, somebody may say, no, it's not. When they say it's not, so they should provide an alternative. So if it is not going to be less than three months, if you like, not means the complement of this one. So not means that sigma can be equal to 3 months, or sigma can be greater than 3 months. So what you have to do is you have to go back and pick another sample and investigate the challenge, if you like. This testing a challenge, okay, or a claim, we call it hypothesis testing, or the test of a hypothesis. So that would be, again, something quite interesting that would confirm your result. So at the end of that test, you may be able to reject the claim or the challenge, or you may have to, accept it. Not accept it, but you may not reject it, if you like. So this is going to be called test hypothesis. It's quite an interesting one. Setting up that test takes a little bit time, but at the end, it's very nice and easy one. And then we have to consider all the cases that we take over here. So we have to test a proportion. We have to test, something regarding to a mean, two cases, when the sigma is given or not. And the last one is a standard deviation. Okay, that's it. We hope to be able to do all of them, and we usually do. So we try to do as much as we can before your quiz so that we can test it on the quiz. And then we are ready for it to get these numbers. Okay, that's it. Any question? So read it carefully. I'll check the assignment. You should be able to do all the assignments regarding to the confidence interval, which is 7.1, 7.2, and 7.3 over here. It's going to be anything else, I'm going to reschedule it. We are going to have only maybe 2 or 3 more sets of assignments for the test hypothesis. And I think that's from chapter 8, and then we're done.